Welcome to the second derivative test. So I'm going to have to apologize right off the bat. I have the hiccups and I can't get rid of them. So I'm just going to make the podcast anyway and hope for the best. So we're going to answer the question here. Where's the function concave up? Where's the function concave down? All right. So this would be a little bit more complicated if I didn't leave the words up, down, and the green dots in there. But since I'm answering this question myself, rather than asking you, I figured I would just leave that stuff in there. So we're going to consider this on the closed interval. All right, so the last green dots there indicate the end of the interval. And so we're concave up, right, where the function is, where it's open upwards, right, like a cup. So that would be from -3. And we're just waiting for the pen to write, -3 to -1. Right, and then it's concave down from -1 to maybe a little bit more than 0, or maybe at 0. We'll put it at 0. -1 to 0. And then it's concave up from 0 to 2. And then it's concave down from 2 until 4. And if you haven't guessed it, we're going to be looking at changes in concavity. Hence my opening problem. All right, so concavity in the second derivative test. The first derivative, and this is in your notes, and I'll fill it in with my lovely handwriting. The first derivative tells us part of the shape of a graph, namely whether the function is increasing, decreasing, or constant on the interval. This is only part of the story of the function on that interval. A good storyteller will also tell us how the function is increasing or decreasing. So example 1, let f of x be a function such that the first derivative is greater than 0 on some interval. All of these have a first derivative greater than 0. They are increasing functions. Draw at least 3 different ways in which the graph of f of x might appear on this interval. In each case, analyze the slopes of the graph are changing. So here I have a constant. The slope is constant. The function is linear. The derivative is going to be a horizontal line. Right? So the ones drawn here are the functions. All right? And then we'll talk about the derivative. All right, so here our function is something cubic. The derivative, so that's saying the derivative, is a parabola shape, and the derivative is going to be concave up. All right, so notice how we're increasing, but not at a constant rate. The function here has a horizontal asymptote at y equals 0. The slope increases as x increases, but there's no change in concavity. That is always concave up, as opposed to my other graph where I'm concave down on part of it. So I'm still increasing everywhere, but I'm not increasing at the same rate in the second graph. Right? I'm not increasing at the same rate in the third graph either, but there's no changes in concavity. That one is always concave up. So here, all three graphs are increasing. First derivative is positive. However, the shapes of the graph are very different. So the graphs of all the functions, well, they were on the other slide, increase over the interval, but they curve differently and therefore have different concavity. One increases at an increasing rate, another at a decreasing rate, and the third increases at a constant rate. And functions that increase at a constant rate are linear, boring, and really don't require calculus. So important idea, if the derivative tells us how the y values of the graph of f are changing, then the derivative of f of x, or f prime of x, tells us how the slopes of f are changing. So the relationship between the second derivative and concavity on an interval. For a continuous function, f of x on an interval, if the second derivative is greater than 0, our function is concave up like a cup on the interval, and the slopes of f are increasing. If the second derivative is negative, then f is concave down like a frown on the interval, and the slopes are decreasing. If the second derivative is 0, the function has no curvature on concavity, and the slopes of f are constant. So now our second derivative is going to tell us all about concavity. Right, so little box here. Get rid of it. There we go. So now, if we know the signs of both the first and second derivative on an interval, we can know what our function looks like. So we're determining, I have it written all for you, and I believe it's in your notes. Determine the signs of f prime and f double prime for each of the curved segments below. All right, so notice here we have so each one of these corresponds to a different segment, right? So this goes to the one on the left upper. This one goes with the left lower. I should have made them different colors. I don't know. That one didn't show up. Right. This one is the right upper. That one didn't show up either. Oh, there it goes. And this one is the left. Excuse me, the right lower. The right lower. There we go. All right. So for the left upper, as you know, our function is increasing, right? All right. It's getting the y values will be getting larger and larger. But notice they start slowing down there at the top. So our second derivative, looks like I'm missing a line, a little derivative marking here. Boop. I don't know where it went to. There we go. So the first derivative is positive, so we are increasing. The second derivative, however, would be negative. Right? We're increasing at a decreasing rate, so we're going to be concave down. That's like the graph that we had over here. Right? So that second one there, notice that in the first part, I'm increasing, but I'm increasing a little slower and a little slower, and then I'm increasing a little faster and a little faster. So where I'm increasing a little bit slower, that's going to be concave down. All right, let's go back to our little chart here. All right, so if we look at the lower left, right, my first derivative would be negative. So that red line curve, or excuse me, not line, the red curve is part of the graph of a function. Notice that is decreasing. It's going down left to right, but it's concave up. So that means our first derivative would be negative. Our second derivative is positive, right? So it's going to have that shape. If we look at the upper right, again, that function is decreasing. It's decreasing at an increasing rate, however. And so the first derivative is negative, right? Our function would be decreasing. But the second derivative is also negative, and we're concave down, right? So both of those would be negative. And then if we look at our lower right, now we're increasing left to right, and we're increasing at an increasing rate, and we're going to be concave up. So the first derivative is positive, and so is the second derivative. And I don't know why that little prime mark is like floating up in the air there, but here, that looks a little bit better. So we discover the values of x at which the function can change its concavity. Next example will help us discover this, but first we'll have a little definition. So here I have some examples of those same segments. All right, so if you're looking left to right here, and I'll put a little X where I'm talking. So over here, a little check mark is, all right, so we're concave up, we're increasing. That matches the blue section of that little section graph there. And over here, where we're concave down and increasing, that matches the black section. If we look to the next one, where over here, right, that little section there, I am concave down and increasing, right? That matches the black section. And over here, we're concave up and we're increasing. That matches the blue section. All right? So kind of shows you how those translate into graphs. Okay? And so we do have some changes in concavity in our graphs here. So we have a definition for us. Okay, so now we need to discover the values of x at which a function can change its concavity. The next example will help us discover this, but first a definition. So an x value, x equals p, in the domain of a function f of x, is said to be an inflection point of f of x if the graph of f of x changes from either concave up to concave down, or from concave down to concave up at x equals p. The point p, f of p, is called the inflection point. All right, so an inflection point is a point on the graph where the concavity changes. Okay. Inflection points are not the only place that we can change concavity. Right? We can change them at inflection points. We can also change them at discontinuities. So concavity can change at points of discontinuity. And we saw that on the last graph. I'll go back to it. At points of discontinuity. T looks like I'm missing an I, but who knows where it would end up if I try to write it. Let's see. Nowhere. That's where it would end up. Nowhere. I don't happen to my either. All right, so it can also change at points of discontinuity. So let's take a look at the graph over back here. All right, so notice there was a change from concave up to concave down at the vertical asymptote. All right, so here there's no inflection point. Come on. No inflection point, but we changed at the vertical asymptote, right there. And here we have an inflection point, 0, 0. We change concavity from concave down to concave up. So those are the two places where we can change concavity, either at an inflection point or at a discontinuity. And I think the next problem I want to do together in class, because it would be another problem with me answering the questions, and that's kind of boring for me. All right, so we're going to pick up with this, learning about how to find our inflection points and our changes in concavity in class on Monday. And I bet you can guess, maybe you can guess, what you think we're going to do to find our inflection points. What could we possibly be doing? Maybe taking a second derivative? Maybe setting it equal to 0 and solving? Well, we'll find out on Monday. But if you guessed those things, you would be correct. All right, so thanks for watching the podcast on learning a little bit about concavity and about our second derivative test, which we're going to be using in class next week. All right, bye for now.